Now it's time to move on to the third presentation for this session by Jonathan Lenoir. Jonathan is a CNRS researcher at the EDYSAN lab. EDYSAN means Ecology and Dynamics of Anthropogenic Systems. He has a PhD in forest science, and his work focuses on the impact of anthropogenic climate change on biodiversity redistribution, as well as its reciprocal, namely how biodiversity distribution can feed back on climate and modify microclimatic conditions. His team developed statistical models to map the buffering capacity of forest canopies at fine resolution in the landscape. Jonathan, you have the floor.
Thanks a lot, Bruno, for the presentation. So first of all, I would like to thank Sandra for the invitation. I'm really happy to be here today and to present some of the work I do. So today I'll talk about the interplay of climate change and microclimatic variation as potential drivers of biodiversity redistribution. First of all, a little bit of context and maybe just a context in terms of how temperature is really structured in space, which matters a lot for species distribution. Temperature is not the only driver, but it's a big driver of how species are distributed at large scale. And so when you go back to Alexander von Humboldt's work in 1817, he was the first to introduce the concept of isotherm. So the isotherm is basically those lines that you see on these famous maps that maybe you have seen when you were at school. Those are big maps where you have the delineation of temperature distribution because each line connects all the points that receive an equal quantity of heat, like mean annual temperature, monthly temperature, or whatever you would consider as an index of heat. And this distribution of isotherm is, as you can see, very structured in space. From the equator to the pole, you have like a reduction of temperature, but also in mountains ecosystem, from the bottom of the mountain to the mountain summit, you have a strong structure of temperature distribution. And this temperature distribution is highly affected by anthropogenic climate change because, as you can expect, those isotherms will move up and down according to climatic fluctuation. And if you warm up the climate, as we have now been doing for many decades from anthropogenic activities, you will expect an upslope shift of isotherms in elevation, but also an upward shift, a latitudinal shift poleward in latitude. And this is something that has already been reported with already a velocity of 15 kilometers per year, which is quite important in Europe to have a kind of like baseline in mind, how fast those isotherms are moving in space according to climate change, anthropogenic climate change. And the most visible consequence of this is, of course, the distribution of ice. You cannot see the isotherms from your eyes, but you can see how the retreat of ice is going fast during the last decades. This is the example of the glacier of Argentière in France from 1890 to 2015. You have a clear upslope shift of the glacier that is retreating due to climate change. And also, as you can see, the biodiversity here, the tree distribution, slowly catch up on these isotherms. But how fast those trees and the biodiversity is tracking the isotherms in space and time is a big question in ecology. And how this happens, it depends, of course, on landscape configuration, as you have seen in the talks this morning. So what we try to do to answer the question of how biodiversity tracks those shifting isotherms is to build a database where we try to collect all the studies that reported changes in species distribution at many scales, from local to big scales, and also across many ecosystems, from marine to terrestrial, and covering plants, animals, and so on. So as much as we can from the scientific literature. And we build this database that we have called BioShift. It's already available since 2020 in Figshare. So if you want to have a look, this is a free database. And this database is containing information on how fast species have been shifting their distribution in space, either along the elevational gradient in mountain. I was talking to you to this isotherm distribution that is that is quite steep in mountain ecosystem, but also along latitude with here 2 example studies. One marine study where the authors reported a latitudinal run shift along the Pacific and the Atlantic coast for marine ecosystems for many fish species, and also an example of elevational run shift in mountain forests across all the mountains in France for several plant species. Those are just 2 examples, but there is about 250 studies that have been reported such changes in species distribution for many taxonomic groups, for marine and terrestrial, and among those, 57 are covering marine ecosystems. Each time, from these studies, we extracted information on the velocity at which species are redistributing in space, but also we try to extract information on what we call the metadata at the study level, that is, what is the study area that has been covered by the authors, how long have they been studying these changes in distribution, and for the methods they use to assess the distribution changes. And compiling this data together, at the end we ended up with about 30,000 observations of distribution shift at many locations across a distribution range of a given species, usually at 3 different positions, like the leading edge, which is this position in elevation that is the highest elevational margin for a species distribution, or the lowest elevational margin if you consider the trailing edge. Same for the latitudinal distribution along the latitudinal extent. And then the centroid of the range, which is more or less the barycenter of the distribution, where you have the highest abundance of the species, where the core of the distribution is located and how it has been shifting in time. And we have this distribution across many taxonomic groups, but with a clear bias towards some taxonomic groups that are quite charismatic, like mammals, birds, insects, but not all insects, like butterflies, which are super studied in the scientific literature, and so for which we have a lot of information. Looking at this database, what we can show is that there is a lot of variation. Although most species are shifting poleward in latitude and upward in elevation, there is actually a lot that are also shifting in the opposite direction, so downslope and equatorward in both marine and terrestrial ecosystems. And so there is a huge variability that is quite intriguing to look at if we consider that just isotherms will be the drivers of species run shift. The same happens when you look at the magnitude of the shift in terms of the velocity, so how fast species are moving in space, like using here elevational gradient in mountains across northern the northern hemisphere or the southern hemisphere. So there is more data in the northern hemisphere because of a lot of studies from the northern hemisphere, with also a legacy of long-term data that is greater in the northern hemisphere. And so we get this huge amount of data from the northern hemisphere at trailing edge, run centroid, or leading edge for many taxonomic groups like plants, cryptogams, and phanerogams, or animals, ectotherms or endotherms, with the different colors here. And the velocity at which those species are shifting in elevation, so how fast they move upslope or downslope, was related to how fast the isotherms were also shifting during the same time in elevation. So did they follow the isotherms? Not so well, because you have the dotted line that is a y equal x relationship, so there is a complete tracking. But one dot here is a species shifting a given amount of elevation, and you can see that there is a lot of variation, negative shift, positive shift, whereas most of the velocities of isotherms are positive, of course. Some are negative, but this is very few. And so there is a lot of variation in this database. So now we wanted to ask, okay, if temperature is not the only driver, maybe we should take into account other climatic drivers and use a different approach, like climatic niche models, also called species distribution models in the scientific literature. It's a tool that is a lot used in landscape ecology also to try to assess how species may shift inside a landscape window. And so we compiled another database from another group that is from the US Geological Survey. They also did a database on species run shift. And so we combined ours with their database to make a unified version, so to have a consolidated version of bioshift. And we looked only here in this specific study on the latitudinal shift from the equator to the pole or in the opposite direction. And so we extracted all the data from this database, and we'll try to confront the expectation from climate niche models, including not only temperature but other variables like precipitation, to the observation or how fast species have been moving in space from those reported studies. So here, if you see, you have like one specific scientific publication. The authors reported run shift, for instance, in France for some butterfly species. They looked at the trailing, leading, and centroid of the range over time since 1980 to 1995. They had the specific methods to assess the shift and so on. And what we did is to use SDM with many climatic layers, not just temperature, but precipitation and other bioclimatic variables over the same time period, over the same study area, and try to assess from SDMs what would be the expected shift in latitude for those three positions in the range. So what the models, the climate-only models, tells us in terms of expectation. And confronting the expectation to the reality, we try to see if there is a good match or a mismatch. And so here, what we did is actually to make sure to foster the SDM so that there is, for each species by study combination, we have a different SDM that is covering the same period and the same study extent to the reported studies. So we try to follow the metadata from the original authors. And what we then looked at is the mismatch and the match. So here on the x-axis, you have the modeled latitudinal shift from the SDMs, from the climate niche only model, climate only niche models, and then the documented shift from the bioshift database. And there is different possibilities. So the zero is in between. If you have negative shift in both the model and the observed shift, you are here, and both positive is here. So you have an alignment between the prediction and the observation. Those are aligned. But then you have cases, of course, where you could have misalignments in yellow. So you predict something, but it's happening in the opposite direction in terms of where species shift up, towards the pole or towards the equator. And when we also looked at the mismatch in magnitude, in addition to this distinction between aligned and misaligned. And then among the aligned species, there are those that are overshooting, that are shifting faster than the climate niche model will tell, and those that are lagging in green, so those species that are shifting in distribution, but much slower than what would be expected from the climate-only niche models. And so we have these three different cases for which we look at the mismatch, so the difference between the model shift and the observed shifts and the absolute value, and this is what we are studying. How this mismatch for those three cases is explained by species trait, landscape connectivity, by methodological attribute or variability in terms of climate fluctuation over time. What we found out is that most of those shifts are very idiosyncratic related to the model shift. As you can see, there is a poor relationship between the observed shift on the y-axis and the model shift on the x-axis for terrestrial and marine. The match is a little bit better for marine. So if you look at those insets plot here, this is a proportion of misaligned and aligned shift. So the misaligned again is yellow and the aligned shift are in purple. And as you can see, there is more aligned shift for marine. In total, 76% of the shifts are aligned between the model and the observation. But still a lot are misaligned, and much more are misaligned for terrestrial. When we aggregate the data at the study level, so lumping together all the species from a given study that has reported run shift, the match is a little bit better, but there is still a lot of variation. So just to say that the model and the climate-only niche model do not improve so much the expectation in terms of, the match between observed and predicted shift. And this is just when we look at those that are aligned in direction, so these two cases of lag and overshoot, there is more cases of overshoots than of lagging dynamics. So most of the species have been shifting faster than the climate niche model tells us. According to what we found out, there is a higher proportion of species that were overshooting the prediction, 62% against 38% for the lagging responses. And then trying to explain this mismatch on those three cases, what we found out as a very important driver was the SDM prediction quality. This was expected, but it was nice to control for it. So when we improve the model performance in terms of one index that we use, that is a continuous Boyce index, when we use this metric, we see that the mismatch decrease quite significantly for the lagging dynamics. And so when you have SDMs that are better fitted, it gives better prediction that are better matching with the observation. The mismatch also decreases with the study duration. So when you have a long study duration, long-term data, then you have better match between prediction and observation. But there is also an increase, a link with the variability in climatic condition over time. So the more variability you have over time, over the study period, the higher the mismatch. So climatic variability decreases the match between the prediction and the observation. And then there is a latitudinal extent also that increases the mismatch, because if you look at big study areas, you have more chances that it doesn't match with your prediction. You have much more variability across a long latitudinal extent. And then the mismatch was also decreasing, which was interesting according to landscape connectivity in terrestrial systems. Those results are only for the terrestrial. I don't show you the marine, but we found also similar patterns. And landscape connectivity is a driver that decreases the mismatch. So then to discuss this result, because we were expecting a better match somehow, one point that could explain why we didn't still find a good match between the prediction and the observation in terms of climatic condition is that even though we included more than just temperature and the isotherm, there is still a mismatch, but because maybe the climatic conditions we use are not the ones that species are experiencing in the field. This is the case of microclimate. I'm coming to microclimate here because if you are like an understory plant or a little mammal living in the soil, burrowing in the soil in the forest, you won't experience the same climatic fluctuation as the weather station data that is located outside the forest in a windy place, usually close to a place where you have like aircraft landing. There is a lot of weather stations that are around these areas that are fully open because you have a lot of air circulation. And this is what the meteorologists and the climatologists on the long term want to catch. They don't want the noise of the microclimatic processes happening near the weather station. But as ecologists, we are interested in these very little fluctuations inside the habitat where species are living, which is very different. And if you consider those microclimatic fluctuations over space and time, which is complicated because microclimate is not just tiny space and fine resolution in time, it's more than that. But it somehow encapsulates this spatial effects. If you consider forest ecosystems, in a meta-analysis, we have shown that the difference between the temperature inside the forest habitat and below the canopy can be much greater than the amount of climate change itself. So you can have like 2-degree difference in temperate ecosystems between inside and outside on average for the maximum temperature of the day. And the same, but even greater for tropical ecosystems. In tropical forests, the difference can reach 4 to 8 degrees, depending on the condition, between the maximum temperature inside the forest and below the canopy compared to outside. So this is huge. It's not just a few, not even, it's more than a degree and quite a lot for microclimatic processes. And so we tried to incorporate those microclimatic processes in species distribution models that I was just mentioning before, to try to see if we can improve those accuracies from SDMs. And we use these microclimatic layers for forest ecosystem in Europe that we generated. So those are maps at 20-meter resolution across the whole of Europe. The black area are the non-forested area of Europe, so you only see the colors of the forested area in Europe. For different bioclimatic variables of temperature, like mean annual temperature, temperature seasonality, and so on. We use those climatic layers to feed SDMs for forest understory plants. We did it for 140 species in Europe. And when we do that, the SDM that incorporate those microclimatic layers does improve a lot the accuracy in terms of, again, the Boyce index, the continuous Boyce index, which is just a statistical metric for assessing how good the SDM predict in the end. And so incorporating microclimate not only improves the mean SDM, the mean quality, but also decrease the variability compared to macroclimatic layers that are based on weather station data. And when we try to aggregate the microclimate into similar grid size as the macro, but incorporating microclimatic processes, if you want, at coarser resolution, it's a mix of the two. It's something in between. It incorporates a bit the microclimatic process, but at coarser resolution, because we are lumping together at a higher resolution in space this microclimatic information. Because here you have a 20-meter resolution. Here it's 1 kilometer. Here it's 1 kilometer. So of course, spatial resolution plays a role too, not only microclimate. And not only it is affecting the quality of the SDM, but it also affects the response curve of species, because if you consider those coarse grid SDMs at 1 kilometer resolution for the macroclimatic grid, this is a patch of forest habitat. So below the canopy, if you just look at weather station, this is what you will get as an information, but it doesn't incorporate what's happening below the canopy, the cooling effect of trees, because trees, they transpire water, so it will increase the capacity of the forest to decrease temperature below. But if you incorporate those microclimatic processes at finer resolution, 20 meters, for instance, below the patch of this forest, then suddenly the SDM response curve is much narrower in breadth along temperature. This is just a temperature gradient. And then it shifts also towards cooler optimum condition, because the forest canopy, the condition below the canopy, is on average a little bit cooler during the vegetation season. For vegetation plants, that is there when the vegetation season is good, this is not the same optimum as what will tell us the macroclimatic models. So just to say that this is important as a conclusion to incorporate microclimatic processes, because it also improves the SDM quality. And I have just shown before that SDM quality matters to improve the match between the prediction of front shift expectation based on climate only and the observation we have from the bioshift database. And so just as a perspective on what we want to do next is to improve the bioshift database further by releasing a second version where we will incorporate these velocities of climate change at a much finer resolution, and with the aim to at some point incorporate microclimate processes in those prediction and expectation. And with this, I would like to thank all the collaborators that contributed to this work, and of course all of you for your attention, and I'm happy to take your questions.